If we're looking at thermodynamics, we really have to start by returning to the mechanical equivalent of heat. And this was the kind of thing that James Joule did, and his name was obviously lent to the unit of the joule. Now, James Joule's experiments went like this. Here is an insulator that takes this system and insulates it from the surroundings, preventing any energy exchange with the surrounding environment. That means all energy exchange has to take place between this rotor, this little propeller that's sitting inside of this water, and the water around it. Now this system has a pulley attached to this mass. This mass, when dropped, will pull this pulley around and rotate this rotor, and that will translate energy from the mechanical system into the water. That temperature difference then will be measured by looking at this thermometer. This is rather nice, as if we look at our basic mechanics, we can look at the energy that gravity will provide, the gravitational potential energy. So by dropping this mass, we will be able to equate mass times gravity times height to the energy that's imparted to this water, and then look at how much of the energy from this rotor, from the agitation caused by this rotating propeller, was translated into heat energy inside this water. So really, what we're doing here is doing work. Gravity will do work on this mass as it drops and translate that into energy inside this container. So as a little review, let's just go back to simple machines that you should have looked at during mechanics. The purpose of a very simple machine is to do work, and when we're talking about work, what we're really doing is reducing the energy required to, say, move an object in space. It does result in a reduced displacement. So if we apply a machine to heat water, for instance, we will see a conversion of mechanical work into heat within the system. And our definition of work was, of course, a scalar quantity, work, which was in Newton meters. A force times a distance. So work is force times a displacement. So we can take our mass here at time 1 and then move it by applying a force to another position. So it's been displaced through a distance s. That will be the definition of our work. We can, of course, say that work is the change in kinetic energy as this object is moved from one place to the other. So final kinetic energy minus the initial, or half mvf squared minus half mvi squared. We can also define power, which is given in the unit of the watt. So be careful not to mix up work and the units of power. So this is the average power here, and this is the work divided by the amount of time it took to do this. So this will be in joules per second or watts. We can actually think of work as a displacement, as we discussed before, so we can substitute in for this W. So power is delta W, the change in work, with delta T, the change in time. This can be equal to F times S over T. Of course, delta S by delta T is a velocity, so we can rewrite this equation as force by velocity, which is an unusual expression to see in terms of mechanics. So what we'd be looking at there would be the individual velocities of these objects. And as mentioned, power is measured in watts. I'm happy with you using the joule per second, which I believe is less likely to be confused with work. It can also be, of course, 1 kilogram meter squared per second cubed, which is the definition here of the joule placed into this equation, placed into this unit. This can get a little complicated to track your units sometimes if you plan to do that. But we're more concerned about looking at heat and work here. We've talked about the mechanics situation as a bit of a recap from something you should have already seen. But we're talking about doing work and translating it into heat. So when we do work on an object, we will change its energy. The heat transfer is a method of changing an object's energy. So we can do work on something and translate that into heat, changing the heat energy of this object. Taking heat and doing work is a little bit more difficult. This will mean doing something such as heating water into steam, causing a piston to be pushed as the volume of that steam changes, and then translating that into some kind of usable work. So it's a little more difficult. So think early steam engines. Here we would provide steam into a cylinder. That would cause the gas inside the cylinder to expand, pushing the piston upwards and then driving the mechanisms. Modern equivalent of this would be something like a turbine, turning a generator at a power station. What we're really doing there is providing steam, running it through a turbine, and then generating electrical energy, taking heat and getting work out, which requires extra linkages and is often quite inefficient in its own right. And of course, something we've already talked about, the molecular kinetic energy of any particular gas or liquid or whatever we are using. The kinetic energy here will be half kT. So if we are dealing with gas molecules, individual molecules can have higher or lower kinetic energies than the average value. This will give you your average Ke, 1/2 kT, where remember K is the Boltzmann constant here, or rather Kb. And when we dealt with gases, remember our total kinetic energy of molecules in our gas are half mv squared, which equals 3/2 n, big N, kT, or 3/2 little n, RT. Ideal gas constant, Boltzmann constant. So let's define the state variables that we really deal with. And these are things we've again seen before. Well, our state variables are pressure, which can vary, V, volume, which can vary, and temperature. And in our ideal gas law, the state of n moles of gas is really determined by looking at these three states. So let's get into looking at the first law of thermodynamics. And really, the first law is just a restatement of the conservation of energy, just solely in terms of energy in a thermal situation. So basic conservation of energy says energy cannot be created or destroyed, just converted from one form to another. The first law of thermodynamics says the change in internal energy of our closed system is equal to the sum of the amount of heat energy supplied or removed from the system and the work done on or by the system. What that really means is any system is going to have some internal energy which is given by the symbol U. We can then do work on the system or we can do work by the system, and that means we're either adding or removing heat from the system. So it really is an energy budget. Are we adding heat or removing it? But in our process, the total energy of the system has to remain the same. That is the basic tenet of the conservation of energy. So let's talk about the internal energy here. The internal energy of our system is given by the symbol U, and it's the total of all the energy of the molecules in our system. So U, the internal energy of any system, will increase if work is done on the system or heat is added to the system. The other way around, U will decrease if work is done by the system on something in the surroundings and heat flows out of the system or heat flows out of the system. So, what does this mean in terms of quantifying our work and our potential energy? If work is done on the system, work, W, will be negative and U will increase. Q is heat added to the system. This means because heat is added, Q will be positive for heat added to the system. Q will be negative for heat leaving the system. And these signs become very important in the equation I'm about to show. It's a simple equation, but these signs have to be adhered to in order to correctly interpret your solution, your answer. So, by conservation of energy in our thermodynamic cases, if a system changes from some initial state to some new state, the change in its internal energy, delta U, is given by Q minus W. The heat added minus the work done is equal to the change in our internal energy. These are all energies, so your answer should come out in joules. There are other ways of looking at this. Delta U here encompasses a couple of things. Delta U is usually a combination of kinetic energy and potential energy. Think back to our discussion of phase changes when we were melting ice or vaporizing liquid water. There was a combination of kinetic energy and potential energy in our system. So this is U, and this is equal to Q minus W. So Q essentially is the heat added to the system here. Work is the net work done by the system, or on it, of course. The signs of Q and W, as I said, are important. So this is the equation you should use with the following signs used that I'll show you in the next slide to modify your expression. If we add heat to our system, Q must take a positive value. If we remove heat from our system, if Q is lost from the system, Q must take a negative value. Work is done on a system, work has a negative value. If work is done by the system, work has a positive value. So this is all based on whether Q or W is going into or out of our system. If you use these signs with the previous equation, this is how you should interpret each case. And this really means looking at your questions very carefully, reading the question carefully for these words. Is the work done on the system or by the system? So let's take a look at an example. Here we have an amount of heat of 500 joules flowing into our system. 250 joules of work is done on the system. What is the change in internal energy of the system? Now, based on what I just said, you should really pick up on one tiny word here that changes the complexion of this whole question if you get it wrong. What is the work done on the system? The work done on the system here is 250 joules. This will change the answer if you're looking for the internal energy. So, what's the change in internal energy of this system? Our heat added to the system is 500 joules. The work done by the system will be negative 250 joules because the work done on the system is 250. This means as 250 joules of work is done on the system, this will equal 250 joules of work done by the system. So you do have to seriously consider the conservation of energy here. So now delta U equals Q minus W. We're saying here now that delta U will be 500 joules minus 250 negative 250, which will give us 750 joules. Now let's take a look at that again, but here with one subtle change. This is the same question. An amount of heat of 500 joules flows into a system and 250 joules of work is done by the system. What's the change in internal energy of the system? So let's do this again. Here an amount of heat of 500 joules flows in and 250 joules is done by the system. What's the change in the internal energy? 250 joules of work is done on the system, so negative 250 joules of work is done by the system. This means in our equation delta U is now going to be Q minus W. We've got 500 joules minus positive 250. This means if we're looking at the change in internal energy when the work's done by the system, we're looking at positive 250. 500 minus 250 joules. Now, because we're using a conservation of energy system, we can actually draw lots of equivalences. If we think back to our situation when we looked at Q equals mc delta T, and we talked about the situation involving the Q equals mc delta T equation, where we looked at the heat that was transferred by calorimetry from a bullet that was fired into a fence. So we looked at this where Rick shoots at the zombie and misses. So he shoots at the zombie and hits the fence. Now we can say, in a slightly different version of that solved before, that Q here is equal to work, which is equal to delta U. So the work done on the bullet here is going to equal the amount of heat that's transferred, which is delta U. We can say that delta KE, the change in kinetic energy, plus the change in potential energy here are going to be equal to 0. We're going to say, somewhat incorrectly, because there would be sound and vibration and other losses of energy, but we can't really account for those. So we're going to get a good guess here as to what the kinetic energy was. We're going to say, because Q equals work equals delta U, that delta K plus delta U is equal to 0 by conservation of energy. That means we're setting our kinetic energy equal to the change in potential energy. That means we can use half mv squared in this case to calculate the actual value we need. These were from the previous slide. This is the mass of the bullet, 2 times 10 to the minus 3, and this was the speed of the bullet from our previous example, which will give us 240 joules. So it's quite useful that the first law translates straight into our old idea of looking at conservation of energy. So here we said the kinetic energy was basically equal to the heat that would be added to this fence. Now, things become a little different when we're looking at thermal processes in sealed systems. And this is where we really have to take stock of our work and our energy budgets. So here, we're looking at isothermal processes. In an isothermal process, we're saying that temperature does not change. Or in other words, delta T equals 0. So we're here discussing the kind of science that was really pioneered in the early days of such things as steam engines in the 1700s and 1800s. So, isothermal process is any process where delta T, change in temperature, is equal to 0. For an isothermal process, we're going to assume that our system is in contact with a heat reservoir, so there's always heat being supplied to it. We're also going to assume that our system is in equilibrium throughout our particular experiment. A typical example for the first law is to take a cylinder filled once again with an ideal gas. This gas is placed in this cylinder with a movable piston. Now this is an ideal gas, so when you see that you should immediately think about PV equals nRT, the ideal gas law that must be obeyed in this situation. If we move this piston, of course, we can change the pressure inside this vessel and we can change the overall volume. But we are here dealing with an isothermal process, so we're keeping the temperature of the system constant, probably by supplying heat from a reservoir, putting a flame underneath this or some other heater. And what we can do for an isothermal process in which we're varying P and V is look at what we call isotherms. These are these lines that we can trace on a PV graph. So here we have a system at a high temperature, and we can say that this temperature is the same throughout, but P and V are going to vary here, and that gives us a specific curve. If we're to look at a system at lower temperature, the graph won't be identical, but it will follow the same basic form. So if we look at A prime and B prime as points on this graph, the system at lower temperature is just slightly shallower and lower down on this P scale and on the V scale. So the lower curve here joins points A prime and B prime, and the upper curve at higher temperature joins A and B. But both of these lines would be referred to as isotherms. The temperature is the same on any point of this line, but P and V are varying. So if you think back to our combined gas law, this is a case where T is staying the same, but P and V are allowed to vary. So for an isothermal system, T remains constant. So the work done by the gas in expanding and pushing the piston must be done by the heat added to the gas. Think about that a little bit and what that means. It does make sense, but think about the wording and convince yourself that this is true. As the internal energy, delta U here, is going to stay constant, we can say this has got to abide by our ideal gas laws and say that delta U then is going to be 3/2 nRT, which is equal to 0. Delta U equals Q minus W. So in this particular case, because it's the work being put into the system here that's changing this system, work here is equal to the heat that's added to the system. So again, think about this wording. Look at the PDF version of this slide and think about the way this is worded and read such examples in the book to convince yourself what's being said. So in this case, we have an ideal gas that's going to expand isothermally. So T is going to be the same before and after our process. And this is going to do 4.3 times 10 to the 3 joules of work as it's expanding. Let's find the change in internal energy of the gas. Well, this is a bit of a trick question in some ways. There's no temperature change here. We're looking at delta T being 0. Delta T is going to be the same at the beginning and end of this process. So delta U, the change in U, is also going to be 0. Again, make sure you can convince yourself of this result. Part B, let's say what is the heat absorbed now during this expansion? Well, we can say that delta U is equal to Q minus W. So there is no temperature change, remember. That doesn't mean that heat has not been exchanged, it just means T stays the same. So we can say that Q is delta U plus W. We want to know what Q is. So rearranging, Q is delta U plus W. We know delta U from part A is 0. That means that Q is essentially equal to the work that's done, 4.33 times 10 to the 3 joules. So this gives us a few rules. If heat is added to the system, then the internal energy of the system will increase. If heat leaves our system, the internal energy of the system decreases. If work is done by the system, then internal energy of the system decreases. If work is done on the system, then internal energy of the system increases. I wouldn't suggest necessarily memorizing these rules, but understanding them and what they represent and how the language here, by and on, in terms of work, might change your system and might change the equations that you use. And that's one of the reasons I say look at the examples in the slide, look at the examples in the book, and think about work being done by or on a system and how that changes your equations in terms of delta U, Q, and W, and assigns the correct signs in each case. So we've looked at isothermal systems. Let's now look at an adiabatic system. And what do we mean by an adiabatic system? For an adiabatic process, this is one where there's no heat flow in or out of the system. In our previous case, for the isotherm, heat was pumped into the system to maintain a single temperature. Adiabatic does not have any heat flow in or out of the system, so our reservoir is essentially cut off. And this is what we would see in a PV graph, a pressure volume graph that we've looked at before. Here is our isothermal system, and here is an adiabatic curve. So, for our adiabatic process, we're going to say here that Q is equal to 0. Remember, no heat is flowing in or out of the system, so Q is equal to nothing. So, in any adiabatic process, no heat is transferred. Q is equal to 0, so delta U is equal to 0 minus W. That means in these cases, delta U will be the negative of the work. If the work is negative, as the gas is compressed, work will be done on the gas. Delta U will increase and result in a temperature rise inside the system with no more energy added to it from the outside. So, if we take a look at this particular graph, here's pressure again, here's volume, the same graph we saw previously. If we start at A and move to B, we're on an isothermal line here. If we're on this line, the adiabatic line, we can go from A to C, and we can see how pressure and volume relate along these lines. So if we go from C to A, volume here is decreasing, and P, pressure, is increasing. Delta U, our change in internal energy, is equal to the negative of the work. So work here is done on the gas, and possibly causes it to combust. And there are engines that rely on this particular process, so we know this to be true. So in an adiabatic process, no heat, as we said, is added or removed from the system, and so by the first law, delta U of a system undergoing an adiabatic change is equal to negative of the work. So as U is proportional to temperature, work becomes negative delta U, which is equal to negative UF minus UI. So this is our change in our potential energy, the negative of the final potential energy minus the negative of the initial potential energy. This will be equal then to minus 3/2 nR delta T, TF minus TI, based on our ideal gas laws. So we can just say this is negative 3/2 nR delta T. In cases like this, a gas expands so quickly that no heat is transferred within this system. And a typical example of this, where we can see this working in a practical fashion, is something like a CO2 fire extinguisher. In a case like this, you have a pressurized container of carbon dioxide gas. When you release the gas and it comes out into the atmosphere, it will expand at atmospheric pressure, causing the temperature around the environment it's spread into to drop as the gas expands. So here's an example where Godzilla is being sprayed down as the actor in the costume has gone up in flames. And as you can see, the gas is exiting the pressurized CO2 cylinder, and as the gas is expanding, it's taking away the heat from the system and transporting it from this system and putting out the fire on Godzilla. And it's by this principle that diesel engines also operate. So not only can we look at a system such as a fire extinguisher expanding in this particular adiabatic fashion, but we can also look at this in terms of engines. And here as per a lousy joke, is Vin Diesel as an engine. So in a diesel engine, what's actually happening is a fuel-air mix is rapidly compressed. As this is done adiabatically, this causes an enormous temperature rise. The increase in the temperature is enough to actually just ignite oil. You do not need some form of spark or a flame or anything else in order to cause this combustion. It's the adiabatic compression of the oil that causes this combustion to occur and a small explosion to drive your piston. And as you can see, we have the pressure and temperature gauges here showing how this varies. This means you can have a combustion engine that doesn't have any form of flame or spark to ignite your fuel. It's simple compression that causes this combustion and drives the engine. So let's take a look at another adiabatic process. Here we have 0.35 moles of an ideal monatomic gas in the cylinder of an engine. It's going to expand rapidly and adiabatically against the piston. During the process, the temperature of the gas drops from 1750 Kelvin to 450 Kelvin. How much work is done by this gas? So you have to think about a couple of things here. How much work does the gas do? Well, what's happening to the pressure? Well, the pressure is varying. The pressure is not constant. So you can't really use work is equal to P delta V here. That would be the wrong direction for this particular problem. But we can use the first law to find work. And then we can get delta U from delta T by setting Q is equal to 0, because we do know this is an adiabatic process. So again, read your question carefully. Adiabatically, this gas expands in the cylinder of the engine rapidly and adiabatically. This question is leading you to use this solution. If you just simply plug things into formulae, you could make this mistake. So how do we do this? We have 0.35 moles of material. We have 1750 Kelvin to 450 Kelvin. Delta U is UF minus UI. This is equal to 3/2 NR delta T, TF minus TI. Let's substitute in. That gives us 0.35 moles times 8.314 being our gas constant times 450 minus our 1750. That will give us negative 5,674.31 joules. Now we can apply our first law. We said work was equal to Q minus W. We know Q is 0. This means 0 minus 5,674.31 joules gives us an overall positive value here for the work, 5,674.31 joules. So there is this little technicality here that you do have to take into account with the final answer. So even though delta U is this, we do have to substitute it into here and say, well, I have delta U and this is essentially my final answer, but what's the effect once I substitute into the work equation of work equals Q minus U? And just to break the long discussion, this is not a diet bat, as people often said in a previous class. Somebody kept pronouncing it as a diet bat. This is a diet bat as a bat eating a taco. This is an adiabat. This means our system here is slightly different to our isothermal when we look in our PV graph. So we've talked about adiabatic systems, we've talked about isothermal systems. We can also have an isobaric system. And an isobaric system is a case where the pressure is now held constant. And if you look at more technical maps of the atmosphere and weather maps, you can actually see these lines. And these lines are referred to as isobars. Anywhere on one of these lines is a line of constant pressure in a weather map. This all too often has been replaced in modern weather maps with people sticking little pictures of happy suns and sad clouds on them. This is a much more scientific way to look at the regions of high and low pressure in the atmosphere and tells you much more about the weather activity in a particular location. So again, back to our first law of thermodynamics, for that is what we're discussing. But now we're discussing it in the context of an isobaric system. So isobaric processes occur where we have constant pressure. You could also see an isovolumetric process. In that case, as per the name, volume stays constant. So again, PV graphs. In an isobaric system, in moving from A to B, this is a line of constant pressure. In an isovolumetric system, moving from A to B, this is a line of constant volume. And these can often be traced for the cycle of, say, an engine or any type of piston which is varying the volume of your system. So if we do look at this in the context that we have done previously as per our piston, here is our piston again, and we have a certain pressure inside this cylinder. We can move this piston up and down and change the volume of our system. So work, if P is constant, is equal to P times delta V. And this is showing the distance that this area of the piston can move. We can relate that to our work, which is force times a distance. This equals to pressure times this area times this distance. This is merely substituting in for force being pressure times area. So if we compress this gas at constant pressure, negative delta V will give negative work. If we expand it, we'll have positive delta V and have positive work. In the case we're looking at here, we're going to compress the gas. If it's compressed at constant pressure, negative delta V gives negative W, so work is done on the gas. In an isovolumetric process, the volume does not change. So now we're switching to keeping the volume in here the same. And this is our equation, works P delta V. If delta V is not there, delta V is essentially zero, no work gets done on the gas, as this side of the equation becomes zero, work is equal to nothing. So in terms of the first law, we can trace out these patterns. Here's our isotherm, going from A to B at pressure A and pressure B, at volume A and volume B. In order to return to this point, it must go through isobaric and isovolumetric part of the cycle. From here to B, isobaric, isovolumetric, back to A, and repeat the system. So processes done with a variable pressure actually give you this kind of graph. And the work that's done by our process can actually be figured out by looking at the area of this curve, of this PV curve relationship that's given on this graph. And this often branches into looking at calculus. You could, without calculus, compare this vaguely to a triangle and have a guess at the work done from this relationship. But really, we should integrate below this curve in order to get an accurate value. And this is where something such as the Carnot cycle appears. Here we have our hot isotherm as our system is heated, and we will look at moving from A to B. We have an adiabatic part of our curve when we move to C, and then we have a cooler isotherm as heat is leaving the system. And the system stays cool, we heat up. Here heat is put into the system. Enter our adiabatic phase. heat is leaving the system, still leaving the system, equilibrated, and heat's going back into the system to cause our expansion. And these are referred to as Carnot cycles, and you'll often see a Carnot engine quoted. That's any engine that operates on this system of expanding and compressing gas. And this will also equal getting work out of or putting work into your system. So in this particular case, we have an ideal gas that's slowly compressed at a constant pressure of 2 atmospheres from 10 litres to 2 litres. And this is the path B to D, this isobaric part of this path. If we look at the total process going from B to D to A, we want to find the total work done by the gas and the total heat that's flowed into the gas. So, this is not as complex as it first looks. So, what's the total work done by the gas? And here's our graph, just for reference. So, work is only done, remember, on the compression BD. We're looking at a case of P delta V, so work can only be done during the compression phase. The pressure is 2 atmospheres. Here we're going to convert 2 atmospheres into pascals, and the work done here, we're looking at the change in the volume, so we're looking at 1 litre being 10 to the 3 cubic centimetres or 10 to the negative 3 cubic metres. So when we look at work being P delta V, we can now substitute in. Here we've corrected for our pressure and we've corrected for our volume, and our volume is going to go from 2 times 10 to the minus 3 to 10 times 10 to the negative 3 cubic meters. This will give us an overall answer of minus 1.6 times 10 to the 3 joules. So what we'll end up with is negative 1.6 times 10 to the 3. So 1.6 times 10 to the 3 joules of work is done on the gas. So when you're doing these calculations, I would seriously suggest, when you're looking at these things, that you quote your final answer as a negative value and then make this statement that work is done on the gas. Here we should have a negative 3 and a corresponding right here for 10 times 10 to the minus 3 cubic meters. But work here is done on the gas. What's the total heat flow now into the gas? And now we're armed with our previous answer. Well, the temperature change here is the thing we have to look at. The temperature at the beginning of and end of our process, B to D to A, is the same. So there's no change in internal energy. That means if we look at our first law, delta U equals 0. This is a cycle. The system goes from B to D to A back to B. So there's no change here. So B to D to A, this is isothermal. Anywhere on this line, the temperature at A and B is identical. So we can say delta U is equal to 0, which is equal to Q minus W. So Q is equal to work, which is equal to negative 1.6 times 10 to the 3 joules. Is that our final answer? Not quite. Q is negative, so that means positive 1600 joules of heat flows out of the gas over this whole process. So it does require you to take a look at these graphs and figure out what's going on in terms of temperature change, in terms of volume change, and how you apply that to these equations. The equations themselves are not particularly complicated, but you do have to get the signs right. Let's look at one final example. Let's look at delta U if we're going to boil water from its liquid state and turn it into steam. So let's determine the change in internal energy of 1 litre of water, which means we have a mass of 1 kilogram, at 100 Celsius. We know this is true because we're boiling our water. It's fully boiled from a liquid to a gas and results in 1,671 litres of steam. We're assuming the process here is done at atmospheric pressure, so we have a bit of information. So, something we can immediately do to save ourselves some time and hassle is we know that this thing is going from liquid water to gas. So we can use the latent heat of vaporization for our system, or LV is 22.6 times 10 to the 5 joules per kilogram. We know then that Q is equal to M times L, LV, which is 1 kilogram that we know we have from the question, times 22.6 times 10 to the 5. So this essentially just moves things around a little bit, and we end up with 22.6 times 10 to the 5 joules, because we really have 1 kilogram. That means the work done by the water then, at this particular constant pressure, is work is equal to P delta V. We know that the system expands to 1,671 litres from 1 litre's worth. So we can say here now that here's our atmospheric pressure, 1.01 times 10 to the 5 newtons per square meter, multiplied by 1671 times 10 to the minus 3. This is our atmospheric pressure, minus, sorry, our volume at the atmospheric pressure for the steam, minus 1 times 10 to the minus 3 cubic meters. So these are our volume, this is our atmospheric pressure, this is our expansion. Here's the conversion. We used 1 atmosphere is 1.01 times 10 to the 5 newtons per square meter, and 1 litre was equal to 10 to the 3 cubic meters. So 1 litre is 10 to the negative 3 cubic meters. So our final answer becomes 1.69 times 10 to the 5 joules. So one on its surface seems to be a question with lots of numbers and a bit of complexity is actually simplified down. We're simply saying Q is equal to mL for our boiling system, and then work is equal to P delta V. Making sure you're in the right units of V and the right units of pressure is the important point. Our final answer is given here. The final answers are not necessarily the most important point. The most important point here is going through this and figuring out what's being done at each step. So our work is P delta V, which is 1.69 times 10 to the 5 joules. Not quite done yet. This means we wanted to find the change in internal energy. So delta U is equal to Q minus W. Q here is 22.6 times 10 to the 5 joules minus this value here, which I've rounded a little. It's 1.7 times 10 to the 5, which gives us a final answer of delta U equals 20.9 times 10 to the 5 joules. Please look through the book and look through the examples done in these slides and make sure you're convinced of these particular values, where we use negatives, where we use positives, and how these processes